All right, so thank you everyone for joining us. So this is a new series that we're launching that's going to be happening approximately every fourth Monday of the month. So please keep us in your schedule. And our goals here, of course, are to try to help fill the gap in current community access to far infrared facilities by getting folks to be thinking a little bit more about exciting things that they can do in the far infrared. So we're trying to provide a platform here where not just astronomers and scientists, but folks involved in current technology and instrumentation, as well as theories and folks across various wavelengths, can talk about what's exciting in the far infrared and what science is strongly motivated by access to these facilities. And so, in keeping far infrared at the forefront of folks' minds, of course, we are really trying to build momentum so that very hopefully, in the next decade, we can again have access to far infrared facilities. So we do have an exciting schedule of talks coming up. So the next talk after this one is going to be February 24th. So we're going to have Irini, who's going to be talking to us about synergies between X-ray and far infrared. And then we're going to have Qi or Coco Zhang from the University of Wisconsin in the next month on March 24th, telling us about really exciting work that's being done with disks, both with ALMA and JWST, but then also how far infrared fills a critical gap between those wavelengths. And then we have future speakers coming up who'll be talking about a wide range of things from time domain to instrumentation to work that's being done right now on precursor grants, right, that are paving the way for future far infrared facilities. So, of course, today we're going to be hearing from Jason. So today, Jason is going to be telling us about PRIMA and an overview of its science capabilities and all of the instrumentation that is motivating these amazing advances. So, Jason, you can go ahead and start sharing and take it away. Thank you.
Thanks, Betsy. So,
And we will post the slides afterward. The talk is being recorded, and it will be available on our website.
all right, thank you, Betsy. So, I am not sure if I'm going to be able to monitor the questions that come in during the talk. I will try to, but if I miss some raised hands, would you interrupt me so that we can address them and not save them until the end?
Yes, and folks, please also feel free to use the Q&A function as well to put in your talks if you prefer not to interrupt and would like them for the end.
Perfect, thank you. So I'll aim to end this within about 45 minutes so that we have time for some questions at the end and so you can get on to your next activity. I know that we've been very busy lately with the AAS meeting and other activities, and so I'm very excited that we actually have a good turnout here today. It's also the beginning of a semester and we have a lot of things going on. So I'll be telling you about the probe Far Infrared Mission for Astrophysics, or PRIMA. The leadership team is shown on in the text here on the right, but I want you to go to our website using the QR code here to see a list of all of our co-Is and other personnel. PRIMA is a team right now. It's not a piece of hardware. It's not even a bunch of drawings. It is a group of people working towards a common goal. And it consists not only of those co-Is, but a very strong formulation team and engineering team across JPL, which is the managing center for PRIMA, and Goddard Space Flight Center, our industry partner, BAE Systems, and IPAC, who will be handling our data processing and archive, and several European partners, including Kinéis, LAM, CEA, Saclay, SRON, Cardiff, and then Northrop Grumman and the Marshall Space Flight Center for telescope testing as well. So probes are a new class of observatory that was recommended by the Decadal Survey and then chosen for implementation by NASA. So a couple of years ago, a call went out for proposals for probes, and 8 were received. 2 were selected to move forward into phase A. PRIMA is one of those 2. It is the far infrared probe. The phase A study started on November 14th, and as of now, it will end on November 14th, 2025. And then there will be a follow-up process with a question and answer between the team and the panel and a site visit. And we expect selection of one of the 2 probes for implementation sometime in the summer of 2026, and then a launch in the early 2030s, depending which probe is chosen. So I wanted to start with why far-infrared observations. I'm hoping that we have people online who specialize in theory or observations outside of the far-infrared part of the spectrum. And there's a few reasons for this, that the far-infrared is important. And one is that star formation and black hole accretion occur deeply embedded in the interstellar medium, which means they're extincted to shorter wavelength observations. And if you want to see the action, you need to look at far-infrared wavelengths, which probe the material in the immediate vicinity of young stars and supermassive black holes, the material that's being accreted onto them, and the material that's being excited by their emissions. The same goes for planet formation. This figure came from the Astro 2020 Decadal Survey, and it shows various areas of astrophysics and where space observations are required, and the far infrared and the rest frame near infrared fall right in that region. With PRIMA, we'll be probing the far infrared, which can only be measured from space, but also the rest frame mid-infrared that's redshifted into the far infrared for galaxies above a redshift of about 1. This provides us the complementary information to, for example, JWST at the short wavelength end, which ends at about 25 microns, and ALMA, which picks up at 350 microns. With far infrared observations, you can not only see that material close to the star formation and the black hole accretion, but you can simultaneously measure the star formation rates and the nuclear accretion rates, and that's only really true in the far infrared. And additionally, you can probe interstellar medium at different temperatures than you can at other wavelengths. An example of that is JWST, which only probes the warm gas in protoplanetary disks, not the bulk of the mass, say in water, which is cooler. PRIMA science is organized around 3 science themes: the origin of planetary atmospheres, how planets get their atmospheres, and how planetesimals build up in protoplanetary disks; evolution of galactic ecosystems, which is really about supermassive black hole growth and star formation, and the quenching of star formation, perhaps by supermassive black hole growth, and the buildup of dust and metals in galaxies. The way we do this is these probes that are specific to the far infrared, which include dust continuum emission, which is responsible for the broad continuum that you see both in the protoplanetary disks and in the 2 lower spectra, which are galaxies, but also a plethora of far infrared fine structure lines, and in the case of protoplanetary disks, a forest of water ice lines. There's also water vapor lines. There are also important solid state features, including water ice and other minerals. And the emission bands of polycyclic aromatic hydrocarbons are redshifted into the far infrared part of the spectrum beyond a redshift of 1, and we'll delve into that a little bit later on. PRIMA's going to be divided up into principal investigator science and guest investigator and guest observer science. And I'll mention now that 25% of the observing time is going to be for PI science and 75% for guest observer science. And of that PI science, all the data will be available just as quickly as can make it available for guest investigator science, which means that anybody can access the archive and use it. And if you're in the United States, you can also apply for funding to support your research. So in this way, all the data are available for the community. And so while PRIMA has to be built to requirements for the PI science, the broad power for community science is also a driver for us. And this is why we're so eager to engage with the community. So why is now the right time for a far infrared probe? Well, clearly there are scientific reasons, which I'll get into, that are being prompted, for example, by JWST. But additionally, we're at a unique time in technological readiness. This is a plot assembled by our collaborator Jonas Muiznes showing the sensitivity of detectors as a function of time over most of the last century. The figure of merit that's on the y-axis is the noise equivalent power in watts per root hertz. The important thing to know is that a lower noise equivalent power is a better sensitivity, so you want to be lower on this plot. And that vertical axis is a log scale covering 10 orders of magnitude. He plots on here various far-infrared detectors with their citations starting in the 1940s, where the work was initially on semiconductors, but gradually transitioning to superconductors in the lower right part of the plot. If you boldly fit a line to these data points, you see that the detector sensitivity has doubled approximately every 2 years for the past 75 years, which is really extraordinary progress. In parallel with that, we've been able to develop larger and larger arrays of detectors from going from one or just a handful early on to arrays of thousands right now. And that's really what's changing the field and making the time right for a probe. In the lower right part of the plot is a green square or rectangle, and that represents the region of time and sensitivity that's important to us now. The red dashed line shows the background limit for resolving power 100 spectroscopy that would be limited by noise from the zodiacal light itself, meaning one has to get below that line such that the detector sensitivity isn't the limiter on the observations. So if you can build sensitive enough detectors and you can cool your telescope to 4.5 Kelvin or below and make it low emissivity, then you can be limited by the astrophysical photon flux noise. And that is the point that we have reached now. The green points on the lower right show an SRON 43 micron pixel and a 200 micron pixel, and JPL detectors at 210 and 25 microns. All of those points fall below this R100 zodiacal light limited spectroscopy. Furthermore, the lowest points actually lie below the photon counting rate at 25 microns, which is extraordinary. So in fact, the end of the road has not been reached for this detector sensitivity yet, but going even further won't benefit PRIMA at this time, and now is the right time for us. So what is PRIMA? It's a 1.8 meter all aluminum telescope, and the warmest optics will be 4.5 Kelvin, and the coolest will be about 130 millikelvin. It will have two instruments. One is the imager that's comprised of a hyperspectral component and an imaging and polarimetry component. The hyperspectral component does imaging with a resolving power of 10 from 25 to 80 microns. This means as you move along the detector array, each detector sees a slightly different wavelength. And when you scan it across the sky, you build up a spectral cube of the spectral energy distribution of the sky. At longer wavelengths, centered on bands ranging from 91 to 261 microns, is resolving power 4 or broadband imaging that comes with polarimetry. And the polarimetry capability is going to be quite extraordinary because of the cold telescope. It'll go much beyond the reach of SOFIA. The other instrument is FIRES, which is a spectrometer. It has a spectral resolving power of about 100, but ranging from about 85 to 130, depending on wavelength, across the entire range going from 24 microns to 235. Additionally, it has a high resolution mode in which the beam is moved through a Fourier transform spectrometer that will have a resolving power of 4,400 times wavelength divided by 112 microns. What that means is resolving power of 4,400 at the HD line at 112 microns and all the way up to 20,000 at the shortest wavelengths that the spectrometer accesses. It's all enabled by these 100 millikelvin kinetic inductance detector arrays, and Primager and FIRES combined will have about 11,000 detectors. The orbit for PRIMA will be at Earth-Sun L2, which is a very low thermal environment, which is important for us. The scheduled launch right now is June 2031. We think it might be delayed to 2032, depending on how the initial rollout goes with NASA. What happens then when you combine these sensitive detectors and the cold telescope? This is a plot showing the time to survey an area of sky, and that area is 100 square arc minutes, to a 5 sigma sensitivity of 3 times 10 to the minus 19 watts per square meter. It's a very low level that corresponds to line fluxes from very distant galaxies. So that y-axis again is logarithmic, covering 10 orders of magnitude, and wavelength is shown on the horizontal axis, ranging from 10 microns out to almost a millimeter. The left part of the plot is covered by JWST, which is shown in the blue-gray line, and there's a sensitivity of MIRI, and then Spitzer IRS, which goes out to beyond 30 microns. On the right side are Herschel PACS, and in the bluish lines, ALMA sensitivities, and these are mapping speeds, not just sensitivities. And in the center are two sets of lines. One is SOFIA, PFLS, and then the bottom, the colored lines are the FIRES and Primager mapping speeds, spectral mapping speeds for PRIMA. And what you can see is two things. One, PRIMA covers the gap in the spectrum between where JWST leaves off at about 25, 28 microns, and almost all the way up to where ALMA picks up at about 350 microns. Secondly, the spectral mapping speed is on par or better than JWST and ALMA, and orders of magnitude better than was achievable with SOFIA, because SOFIA had a warm telescope and less sensitive detectors. This new capability brings opportunities that we haven't had in the past. For example, with the long slits on FIRES, we can observe and map the extended gas in the disks of galaxies or extraplanar gas, and do line intensity spectral mapping for cosmology with far infrared fine structure lines. Additionally, because of the large sensitivity leap over SOFIA, extensive polarimetry mapping will be possible, both to probe the origin of dust and the roles of magnetic fields in the interstellar medium. Further, a deep all-sky survey would be possible with PRIMA in 5,000 hours of observing time, and I certainly hope that this is proposed as a guest observer program with PRIMA. In fact, we've designed the observatory such that it can observe during the several hours a day while telemetry is downlinked to Earth. You could spin the spacecraft and over a period of a year, build up coverage of much of the sky as we go around the sun in their Sun L2 orbit. So I want to focus on a few areas of science, and I won't have time to go into depth on any of them, but there's time for questions, and the whole PRIMA team is available to you if you want to engage in conversations after this. So what I'll do is I'll highlight just a subset of the PRIMA principal investigator science, and then a few of the guest observer cases that have been proposed by the community that I'm particularly excited about. So the first one that I want to talk about is the growth of planets in protoplanetary disks, which addresses a couple of our objectives. And one is to measure the masses of protoplanetary disks, which are currently uncertain to an order of magnitude. And a second is to understand the role of water in planetesimal formation and planet growth. Do I have a question? I think someone has their microphone on. The upper plot is a cartoon representing the structure of a protoplanetary disk. You can see a few things in there. One is the water snow line and the carbon monoxide snow line, and where water vapor is and carbon monoxide gas. The method of measuring disk masses using carbon monoxide is not very effective because it is depleted onto dust grains, and that's what leads to the order of magnitude uncertainty. So to measure the masses of the disks, we want to use the hydrogen deuteride line and 112 microns, and secondarily the 56 micron line, which is neither depleted and is optically thinner. And that will enable us to pin down the masses, which is a key unknown in the formation of planets. The second is to understand the distribution of water vapor. And the reason for this is that it has been proposed, in fact, it's probably likely, that planet formation is driven by the drift of icy pebbles from the outer part of the disk to the inner part of the disk, rather than direct gas accretion onto planets. So what we intend to do is measure the distribution of water vapor, both the warm water and the cool water and the ice throughout the disks. And the way that we do that is that you can see in the bottom plot in the model spectrum of a protoplanetary disk that PRIMA probes both warm and cool water lines. There are hundreds of lines in the spectrum. In fact, it's been shown that you can recover the distribution of the water throughout the disk without resolving the disks because there are so many water lines that are excited at different temperatures. And I can show a demonstration of what PRIMA will do here in that regard. On the left is a plot showing water column density versus disk radius with two models on it. The green model is a model that shows the water column density if there's icy pebble drift in the disks. And the purple solid line shows the case in which there's no icy pebble drift. And the water column density near the water snow line, say at 150 Kelvin, is orders of magnitude different in these instances, which means it should be pretty straightforward to distinguish models of gas phase planet formation versus pebble drift and get to one of the key unknowns in planet formation. The plot on the right shows a model of a protoplanetary disk based on Spitzer and IRAS observations of a number of water lines at different temperatures that would be observed by PRIMA. The gray horizontal line shows our requirement, and the wavelength is on the vertical axis. And what you see is that cold water lines, 50 Kelvin-ish, will be observed. Snow line water, more than 150 Kelvin, will be observed, but also warm and hot water. And these occupy different regions of the disk, which is cooler as you go outward from the young star. This complements JWST, which is really good at measuring the warm water in the disks, but not the bulk of the mass, which shows up in the cool component and is further out where most of the planet formation probably takes place. Okay, I want to talk about a couple of our goals with the galaxy science, but before I dive in, I want to reorient for a moment and talk about what some of the spectral features are in the far infrared that we'll be using to make our measurements. So wavelength is represented horizontally on this diagram, and there's a model galaxy spectrum consisting of dust continuum and far infrared fine structure lines, which are narrow, and polycyclic aromatic hydrocarbon emission bands, which are broader. At the bottom, the galaxy is shown at a redshift of 0, and then at cosmic noon at a redshift of 2 in the middle, and at the top is a redshift 5. instance of the spectrum. PRIMA's wavelength coverage is shown in the highlighted gray hashing with the blue bar at the top. And what you see is we probe the peak of the dust continuum emission, except at the highest redshifts. We also probe the mid-infrared slope of the spectrum, which is important for measuring nuclear activity. And as we get to higher redshift, we also get those polycyclic aromatic hydrocarbon lines, which enables us to probe these complex molecules in the early universe in a way that hasn't been possible in the past. And the important thing here is that we have multiple measures of some of the important parameters that we want, such as star formation rate and nuclear accretion rate. The star formation rate and nuclear accretion rate can both be measured from the far infrared luminosity and the slope of the mid-infrared continuum emission, which is redshifted into PRIMA's bands. So you can simultaneously measure the star formation rate and the accretion onto the black hole in a galaxy. Secondly, using the oxygen 4 fine structure line and a number of lower ionization lines, such as the neon 2 line shown here, you can measure the nuclear accretion rate and the star formation rate as well, and independently of the continuum. And then those far infrared fine structure lines, the brightest ones, start to come into the band just above a redshift of 2. Metallicities that we're interested in measuring in galaxies are going to be in the PI program based on the oxygen 3 and nitrogen 3, lines that are highlighted with the green indicators at the bottom. It is well known that supermassive black hole masses in the center of galaxies are well correlated with the stellar masses in the bulges of galaxies and the stellar masses of galaxies as a whole at a redshift of 0. What's not known is why they're so tightly correlated. The plot on the left shows the correlation in a cartoon fashion with the log of the supermassive black hole mass on the vertical axis and the log of the galaxy's stellar mass on the horizontal axis. And the broad band going from lower left to upper right represents this observed relation in the local universe of black hole mass versus galaxy mass. And the width of that indicates that there's some spread in that distribution. What we don't know is the black hole accretion rates and the star formation rates over the history of the universe that led to that relation that we have today. And it's important because whatever led to it has controlled galaxy evolution, likely by quenching the star formation. So 2 example models are shown on this plot on the left. One is from a Spritz model, which is empirical, in which the black hole growth is slow. And on the lower right, shown in blue, is the Santa Cruz model. It's a semi-analytical model, it's theoretical, which has much faster black hole growth. Our aim is to separate those by measuring the star formation rates and the black hole accretion rates using both the continuum and the far infrared fine structure lines. An example of how we'll do that is shown in the plot on the right, which has, again, log of black hole accretion rate versus star formation rate on the vertical axis and redshift on the horizontal axis, with redshift 0 at the left and 2.5 at the right. In pink are the Spritz predictions, and in blue are the Santa Cruz model predictions. The bold lines are the medians in these, and the colored bands around them are the interquartile ranges because there are spreads in the predictions of the star formation rates and black hole accretion rates. Shown in the smallest error bars are the PRIMA quartile uncertainties. And this is from a dedicated survey of a region of sky in which we measure these rates simultaneously. And what you can see is that the errors are going to be very small compared to the spreads. And given the separation of the 2 models, it should be easy to discriminate them. Neither one may be right, but we'll measure what the real answer is. Additionally, we want to understand the mechanism that's responsible for the correlation in the star formation rate and the black hole accretion rate. And it's been proposed that it is outflows from the active galactic nuclei. In fact, it's been proposed that all very luminous galaxies that have AG in them have strong outflows from their centers. So we intend to look for those outflows in the cool molecular component, which carries most of the mass, to see if it is a likely reason for the quenching. And we'll do that by observing the OH line in a sample of 50 galaxies to measure both the mass and the momentum of the outflow rates. We'll resolve these lines using R of 900 spectroscopy at the 84 micron line. There are actually 4 OH lines that we'll observe with the Fourier transform spectrometer on PHI-RAS. Okay, so I want to talk about the high redshift universe a bit more now. And first, I'm going to do that in an instance of the PI science, and then I'm going to talk about some of the guest observer science that I'm excited about. So one question that we asked is the PAH to metallicity relation that's observed in the local universe valid in the early universe? It's been observed that PAHs are present at a reduced level in low metallicity galaxies in the local universe. This can be seen in the plot on the left, which has the mass fraction of polycyclic aromatic hydrocarbons in dust grains versus metallicity on the horizontal axis. And the measurements are shown as the points, and then a model shown in the black line is fitted to that, which goes out to a metallicity of about 0.4. It turns out that we have very little knowledge of what the polycyclic aromatic hydrocarbon relation to metallicity is beyond a redshift of about 2. So it's hard to make a prediction of what this relation would look like. But if you do shift the local mass metallicity relation in redshift out to 2, then you get the orange line here. Superimposed on the data on this plot are blue rectangles, which represent PRIMA error bars from the observations we intend to make. And you'll see that we'll be able to determine whether or not that mass metallicity relation extends out to redshift of 2 or not, and determine what the relation is, in fact. The metallicity will be measured using the O3N3 tracer, which is a combination of oxygen and nitrogen, which show up in our bandpass at between a redshift of 1.75 and 2.5. The PAH mass fraction is going to be measured from the 11.3 and 12 micron bands. So we can extend to much higher redshift with PAHs than if we use the shorter wavelength emission bands as well. And there's 2 plots here relevant to that. The one on the left shows the observable PAH fraction to total PAH band emission as a function of redshift for both JWST and for PRIMA. The blue curve going from upper left to lower right is is JWST, and it shows that as you go to higher and higher redshift, the fraction of PAH emission that can be observed goes down because the emission bands are moving out beyond the long wavelength limit of JWST. Complementary to that is where JWST picks up at the shortest wavelengths at 25 microns. The crossover is at a redshift of 2, but you could see beyond a redshift of 3 is really the best opportunity for us to measure these complex molecules in the high redshift universe. The plot on the right shows this hydrocarbon abundance, again, QPAH, versus cosmic time in gigayears on the bottom, or redshift on the top horizontal axis. So the low redshift universe is on the right part of the plot, and the pink or peach dashed band shows stacking constraints on the QPAH abundance since redshift of 1 or out to redshift of 1. Then uh, beyond that, there are very few measurements that have been made. And it's extremely difficult to even predict what the hydrocarbon abundance might be. So one model is a cosmological simulation that extends the local pH metallicity relation that's shown in the blue solid line with a spread around it. There's another model that's equally viable at the moment, which has a delayed injection mechanism, and that is the orange line. Superimposed on these are blue boxes showing the PRIMA measurements. So while we don't actually know what the quantity of pHs will be in the high redshift universe and which model is valid, either way, we'll be able to measure it with high fidelity out to redshifts of 6 or 7, and in the instances of lens galaxies, even higher, 8 or more. Another case that was submitted by the community for guest observer science for PRIMA that has me really excited is polarimetry to observe magnetic fields in nearby galaxies. Our community as a whole has been saying for something like 40 years now that we want to understand the role of magnetic fields in molecular cloud evolution and star formation. And there are a lot of theoretical models of this, but the observations are quite few in number and don't constrain the models very well. Towards the latter end of its lifetime, Sophia made a lot of observations that started to impact this, but then Sophia was decommissioned. PRIMA is going to pick up and do a great job with this, with polarimetry from 90 out to 250 microns, but with much greater sensitivity, which means that many, many galaxies can be observed and molecular clouds in the Milky Way, for example. And shown on the left here is a simulation of NGC 6946 using real spire observations and expected polarization with the dashed lines showing the PRIMA extracted magnetic field vectors there. Actually, those are the polarization vectors. The magnetic field vectors, I think, would be orthogonal to those. So in nearby galaxies, we want to resolve whether the fields align with the cosmic ray derived magnetic fields that show up on larger scales. And within molecular clouds, we'd like to tie together the structure that's probed on larger scales, say from Planck, to what's probed on the smallest scales with ALMA, where there's a big gap and where the magnetic field may be responsible for some of the dynamics as clouds collapse to form cores and then protostellar disks. There's a time domain case that has me very excited as well that we weren't able to include in the principal investigator science, but I think is going to make a compelling guest observer case. And that is to understand how protostars accrete their mass. Mass is the fundamental property of stars, but we don't know how their mass is accreted when they form. That is it quiescent or is it episodic? And the only way to find out is to make far-infrared observations and to observe a large number of protostars over a varying range of timescales repeatedly for a number of years so that you can measure the quiescent rate and bursts. And then you can ask the question, does most of the mass accretion occur in rare burst events, which will have consequences for the structure of the disks, or is it in a more quiescent fashion, which is dominated by an average accretion rate? The plot on the right shows the inferred to actual burst amplitude measured from a number of models of accretion onto protostars as a function of wavelength, with space-based mid-infrared shown on the left, space-based far-infrared in the middle with the green shading, and ground-based submillimeter on the right with the tan shading. And the important point here is that to measure the burst amplitude of bursts when accretion events occur can only be done well in the far infrared. And that's because in the mid-infrared, both extinction and orientation affect your inference of the mass accretion rate from the observed luminosity. Whereas at the longest wavelengths, the inferred luminosity is temperature dependent. So it depends on your assumption of the temperature. So you really need to make the observations in the far infrared. And it was proposed that a set of 2,000 protostars be observed on cadences ranging from 2 weeks to 5 years, which is the length of the lifetime of PRIMA, repeatedly to identify these bursts for a large sample of galaxies. And I think that sample of protostars. I think that the archival value of this would be enormous because there's all kinds of time domain things that could be measured. In addition, the polarimetry of these observations comes along for free because it's embedded in the long wavelength observations. And so we get observations of the magnetic fields of all these molecular clouds that embed the protostars to very high signal to noise. So I want to spend only 10 more minutes talking about the detector technology that is enabling this, and then ways in which you might get involved if you think that far infrared science would help the astronomy that you do. So the kinetic inductance detectors are the innovation in technology that enables PRIMA now and the huge leap in sensitivity and detector array size, and therefore spectral mapping speed. What kinetic inductance detectors are micro-resonators. The resonators comprised of a capacitive and an inductive component that's shown in the transmission line schematic on the left. The inductance is variable. It's a portion of the detector in which incident radiation breaks Cooper pairs, which are the superconducting electrons in a superconductor, into quasiparticles or electrons in the normal band. When the Cooper pairs are broken, the kinetic inductance of the detector changes. This is the inductance that arises not from the geometry of the inductor, but rather from the inertia of the electrons themselves. So every photon that's absorbed, on average, breaks something like 0.6 of these Cooper pairs. Actually, it breaks several Cooper pairs with an efficiency of 0.6. And so if you excite these resonators with a probe tone, you can measure the change in the resonance as light is incident on it. And that's what's shown on the right. What's shown is the transmission in dB of a probe tone as a function of frequency, with frequency on the horizontal axis. With no incident power, you get the sharp resonance that's shown at the very right. The quality factor of this resonance would be tens of thousands for PRIMA. As light is shined on the detectors and the Cooper pairs are broken, the inductance increases and the resistance increases a little bit. It becomes partially normal metal. And so the sharpness of the resonance decreases, or the quality factor decreases. And you can measure the frequency shift of this and the amplitude change, and we focus on the frequency shift. And what makes KIDS so elegant is that you can put an array of 1,000 of these detectors down on a chip by depositing aluminum and niobium on silicon, and then tune each resonator to a slightly different internal resonance frequency by changing its capacitor relative to its neighbors. So you can send 1,000 probe tones down the same coaxial cable and read out the entire array with that one coaxial cable going in and one coming out and going to amplifiers. So a very nice, elegant readout process. Here are some prototype KIDS that were developed for PRIMA. In the upper left are flight-like arrays for PHI-RES, which are 24 spatial pixels by 84. These are fabricated at the Micro Devices Lab at JPL, and they have micro lenses on them that focus the radiation on the inductive part of the detectors that were fabricated at JPL. The bottom panel shows polarimetric KIDs developed by Esron and Delft in the Netherlands. These are antenna coupled instead of being absorber coupled. And by clocking the antenna angles in adjacent pixels by 120 degrees, by scanning the array over the sky, you measure all the Stokes parameters every time 3 detectors go over your source. The plot on the right shows the sensitivity requirements for PRIMA's detectors in noise equivalent power again versus modulation frequency. Kinetic inductance detectors are differential detectors. They're not integrating detectors. Or said another way, they're AC coupled. Their signal is constantly changing. They need to be modulated, and they're subject to low frequency 1 over F noise. So you modulate the signal so that your signal band is above the frequencies at which the noise matter. So in NEP, our requirements on this plot are shown in the purple dashed and orange dashed lines. Below that, in the solid lines, are measurements of with SRON KIDs shown in green and JPL detectors shown in purple and orange. And you see that we clear the requirements by a factor of a few. So we have margin there, and that we are able to modulate by scanning the telescope, by scanning the Fourier transform spectrometer phase delay mechanism, and onboard beam steering mechanisms to the signal band where the 1 over F noise is quite low, that is above 10 hertz. So if you find that this is exciting and you want to learn more, here's a number of ways that you can learn more and get involved with us. One, see the website where we've got a list of news, events, papers, talks are archived. And the website shown on the QR code in the lower left. At the bottom of the front page on the website is a sign up list if you want to join our mailing list, and you can get updates of events and our newsletters every couple months. You can submit an application to join one of our working groups to develop a guest observer case or cases. And we have conferences coming up over the next year. The next one will be in Marseille, the end of March to April, and registration is open for that. It's Dusting Off the Secrets of the Cosmos with PRIMA. Additionally, we published a guest observer science case book on the archive. That's the QR code on the lower right. We're currently we'll be accepting papers for a second version of this book because members of the community have come up with additional ideas. Related to that, the JADIS journal approached us about having a special issue on PRIMA, and we took them up on that. And we opened up to the community to submit papers to JADIS on science that they would do with PRIMA. And we identified 2 outside editors to take any perception of bias away from the PRIMA team. And 28 papers have been submitted to JADIS on science opportunities that people would like to pursue with PRIMA. Those will be reviewed by referees over the next few months, and then we hope that the journal will be published sometime this summer. So I'll just leave this website up so that you have the QR codes in front of you in case you want to use your phone to photograph them, and I will take any questions.
All right, Jason, I see one question in the chat from Neil Turner, who's asking you to clarify the FTS module spectral resolution versus wavelength.
Okay. So don't have an image of the FTS here. The way it works is this: the wavelength of the Fourier transform spectrometer is naturally, the resolving power is naturally wavelength dependent. It has a resolving power of 4,400 at 112 microns, which clears our requirement and adds margin to ensure that we can measure that HD line in the presence of brighter lines around it without suffering from line confusion. As you go to shorter wavelengths, the resolving power for a given scan length of the Fourier transform spectrometer goes up. So at the shortest wavelength of PRIMA at 24 microns and Phi-Res, the resolving power is 20,500. Likewise, as you go to longer wavelengths, the resolving power decreases. So you can use this formula on the Phi-Res third box from the top here. Resolving power equals 4,400 times your observing wavelength divided by 112 microns to get the resolving power. Does that help, Neil?
Sorry,
Oh,
I'm muted.
You're muted.
Yes, sorry. So Jason, in case you can't see the chat, Neil says the equation on the slide says resolution decreases to shorter wavelengths.
Oh, in that instance, we have them flipped. So it should be, uh, let's go back. I believe you're still seeing my screen.
Yes.
Okay, 112 microns over lambda. Thank you for pointing that out, Neil. 112 microns divided by lambda is what should be shown in the equation, not what's shown here. Thank you for catching that. What I said was not physical.
A question from Hendrik Lins, who asks, will the Phi-Res high-res mode also instantaneously cover the full wavelength range, or does one have to cover the spectrum bit by bit?
The Fourier transform module covers the entire spectral range all at once. So you do not have to cover it bit by bit, with one caveat. For our slits are separated into two pairs. So to recover the entire spectrum from 24 to 235 microns, you have to make two observations, two different pointings. So it actually takes two observations to get the entire spectrum. Does that clarify?
Dave Leisowitz has his hand raised.
Hi, Jason. I could probably just walk down the hall and ask you this question, but maybe it'll benefit others to hear the answer too. And I apologize if I missed something that you already said. When you were talking about the water distribution, and in particular the frozen component of the water, the line emission you can get at the distribution using what I would call Doppler tomography. The line shape tells you something about the physical distribution of the water vapor. That technique, because of the inherently broad spectral lines of the water ice, their spectral features rather than lines, you can't use that technique. So I was wondering, maybe you said it, are you inferring the distribution of frozen water from the distribution of vapor state water?
We are two things. One, we're inferring the distribution of water vapor, of water from the vapor. And we do that because we have so many water lines that have varying excitation energies that we can recover the entire distribution of temperatures. But in addition, shown in blue on this lower plot here, blue shading is water ice, and we'll be measuring the water ice solid state as well.
Okay, thank you.
All right, so we have another question in the chat from Neil Turner, who would like you to say more about why detecting young star accretion outbursts doesn't work well in the submillimeter, where the surrounding envelopes are optically thin, just based on the Geo book science explanation wasn't being so clear for him.
Oh, it's because you make two things. Oh, that's not what I meant to do. Two things. One, that luminosity of the protostar, the luminosity is temperature dependent. It depends on the quantity of mass present, but it also depends on the temperature of it. Secondarily, the submillimeter observations also really probe the envelope and not the disk region. And the disk is where in the inner part of the core is where the accretion is.
All right, thank you, Jason. Hendrik would like to know, what is the most demanding technology issue to be addressed during phase A? Is it the positive development of the detectors or something else like the cooling of the telescope, for instance?
Oh, that's a neat question. So the cooling of the telescope is in hand because we're using flight spare Miri cryocooler for that. And then we've got in addition, a high TRL continuous adiabatic demagnetization refrigerator to cool the detectors and the cold stage of the optics. The heavy lift on the detectors was reaching the noise equivalent power that we needed to become background limited, which we set as a goal to really do transformative science. So we've reached that noise equivalent power and we feel very comfortable about it. The next important thing that we need to do is continue to work on yield in the detectors, in that we don't consistently get high yield. Some of our detector arrays have high yield and some do not. And it's not efficient to make a lot of arrays and choose the best ones. So what we're attempting to do is really understand the processing well so that we can reliably get high yield, and the screening process is more streamlined that way. Does that answer your question?
Yes, thank you.
So I think we intend to post this talk online, but we'll also post the slides. And thanks to Neil's catching my error, I am going to fix this table right here for the version that gets posted online, but it will be wrong in the talk that's recorded. So hopefully anybody who's watching listens all the way to the end.
All right, so thank you again, everyone, so much for joining us. Since I didn't say so at the beginning, my name is Elizabeth Mills. I'm a professor at the University of Kansas, and so along with organizing PCAST, I'm also leading PRIMA's communications and community engagement efforts. So please do contact me directly if you have any questions or suggestions, and definitely please join us again next month, February 24th, for our next talk by Irini Lambrides about X-ray and far-infrared synergies. And I encourage folks who have questions, for example, about determining water distribution in disks, join us in March for Coco Zhang's talk, where she's doing a lot of this work right now with JWST spectra. And then for more information about detector development, join us in April when Joachim Basselmans will be talking about the detectors. So thank you, Jason, and thank you, everyone.
Thank you, Betsy, for organizing this and managing it. And thank you, everyone, for attending.